let us switch the presentation over to Jennifer Rexford. So Wendy, please make Jennifer the presenter. And once again, Jennifer is again someone who doesn't really need an introduction. Not only is she one of the most well-known names in network performance modeling, she has of late been making significant contributions to P4 and network programmability. So with this very brief and inadequate review, Jennifer, over to you.
You see my slides?
Yes, we can see your slides now.
And we can hear you.
Even better. Hold on. Sorry, my screen just went crazy trying to get my slides back so I can see them too. Great. Thanks very much. What I want to talk about is I hope that 50 years from now, networks will be able simply to do what they're told, that will know how to design and build networks that are worthy of the trust that society increasingly places in them. Now, at some level, this isn't at all a new idea. It's been a holy grail for a long time that we should be able to tell the network what to do. These days, it goes under the term intent-based network management, which is the simple idea that we should be able to describe what we want networks to do at a high level in a declarative way for the network as a whole, and that underneath the network should simply just do it at a low level with specific mechanisms that work across many distributed devices. Now, this has been largely unsuccessful for many years, and so I'm going to try to convince you of in the talk is that we're finally at a point where we actually might be able to be successful doing this. So why has this been hard for such a long time? And part of it is that the network was never really designed with the management of it in mind, that there is always limited visibility into the underlying traffic, the performance of the network, and so on. And the individual protocols and mechanisms implemented on the individual devices were hard to tune. And part of that was because network management had to be bolted on as an afterthought, that you would take whatever data you could get, you would analyze it in whatever way you could to try to infer what was going on, and then you would try to affect change in the network by tuning whatever knobs those network protocols and mechanisms might make available, never quite tailored to the task at hand. So in short, what could go wrong? And there's a great talk that Jeff Mogul at Google gave a few years ago on self-driving, so-called self-driving networks. And he gave the analogy to the self-driving car, that if you're going to build the self-driving car, you wouldn't start with the Corvair. You wouldn't start with a car that actually is extremely difficult to manage, hard to control, unintuitive. And that's in a way what we've been trying to do for many years in network management, is to add on as an after fact management on top of dials and knobs that are not suited to the task. So why am I optimistic that in the next 50 years we'll finally crack this nut when we haven't cracked it for the first 50? And the reason I'm optimistic is the increased emergence of deep programmability from top to bottom and from end to end, from logically centralized software-defined networking controllers down to the local agents running on individual network devices, even down to packet processing in the individual switches and network interface cards. And increasingly, that level of flexibility is available end to end from where users access the network all the way to the services they might be running in a local edge cloud or public cloud. And I think this is really the key, that if you're going to raise the level of abstraction for running the network, you need to have some say over the mechanisms underneath so that they're actually amenable to abstraction in the first place. And in particular, what I'm hoping is that network owners with this newfound flexibility will want to add new dials to their network tailored to the task at hand, to measure traffic performance, detect cyber attacks, detect and diagnose failures, look at signal strength, and so on, depending on what management task they're trying to do. In other words, to design the control loop by deciding exactly what measurements belong in that control loop, and likewise what knobs they might want to tweak to drop or mark or rate limit traffic or reroute traffic onto better paths or hand off a phone from one access point to another, and so on. The main point that's interesting here is the ability to actually customize the design of these knobs and dials to the task at hand. In other words, to design the actual network control loop. And in some cases, maybe even integrate measurement analysis and control, or measurement analysis and adaptation directly where we process the packets. And that's what I'm going to spend a few minutes talking about, just a few examples of this from the work in my group. You know, they're modest examples, they're point solutions to specific technical problems that arise in network management, but I hope they're examples of a larger effort we can make to make networks more inherently easy to manage. So the first example is microbursts. So in data centers or also backbone networks, we'll sometimes see sudden abrupt increases in traffic that may even fill up the entire queue of packets awaiting service on the link. These can be caused by incast workloads in data centers or by cyber attacks on a backbone, and they lead very quickly to high packet delay and even packet loss, even though on a slightly longer timescale, link utilization might be relatively low. So if you don't have the right measurements, you may not even know that these are actually even happening, because on a somewhat longer time scale, the queue lengths and the packet loss rate and the utilization of the link are all relatively modest. And so that's precisely a case where you need finer grained measurement. In particular, you'd like to be able to ask very simple questions, like when a packet arrives, is the queue backlogged? If it's backlogged, what fraction of the packets in the queue are from this packet's own flow? Is this packet part of the responsible flows for the backlog in the queue, like this green packet here? Or is it just an unlucky victim that's only contributing a small amount to the load in the queue? And why do we want to know this? Well, because we might want to take action directly on this packet based on the answer to that question. For example, we might want to drop or mark a packet probabilistically based on its contribution to the traffic that's in the queue, so that we can punish the flows that are responsible for the microburst and mitigate it quickly while not punishing the other flows. This is a relatively simple idea, and you can find papers going back many years proposing these kinds of forms of queue management. The key thing is now we can actually do this because we've got programmable network devices that can efficiently collect this kind of measurement data and act on it directly in the data plane. Something that'd be very difficult to do if you're forced to work with existing measurement data like NetFlow and existing configuration interfaces. To give a second example, let's think about something like denial of service attacks that are so prevalent today. Many of them involve an attacker amplifying an attack by reflecting traffic off of other servers on the internet. So a simple example here is a DNS reflection attack, where an adversary might spoof the source IP address of an intended victim and send short DNS requests to a number of servers around the internet so that the larger responses all hit the victim, and exhausting the victim's compute and server, compute and network resources, and perhaps damaging the network resources close to the victim. So what might you do here? Where again, if you had the right kind of measurement data, you might be able to identify suspected victims and the adversarial traffic relatively easily if you have the right measurement in the right place. A good example is sort of broad class of queries where you might want to ask for a given key, like a destination IP address, how many distinct sources might be communicating with this victim. And if it's above a threshold, you might want to flag this destination as a suspected victim of a particular kind of attack. In this case, maybe a DNS amplification attack. But this same basic measurement structure is also similar for things like super spreaders or port scans and so on. So if we have the ability to ask and answer efficiently questions of this type, we'd be better able to mitigate these kinds of attacks right where they occur. And in particular, we might drop or rate limit packets to the victim, or even transition that victim's traffic over into more fine-grained handling to make sure that responses only are delivered to those suspected victims when it's a response to a previously generated request by that same victim. In other words, some sort of firewall. A defense that you could, in theory, run all the time, but might be too expensive to run for all requests all the time. So again, the ability to put the right measurement in the right place at the right time makes the control loop actually relatively straightforward to specify and implement efficiently. And just give a third example, which is that a lot of networks today have path diversity, whether it's a data center or a backbone network. And so a natural thing to want to do is to be able to distribute traffic over multiple paths in a way that achieves good performance, to find the least loaded path in the network or the path with the least delay, and to adapt to changes in that traffic over time. So here too, if we can actually specify the control loop ourselves, there are relatively straightforward things we might consider doing. For example, we might want to compute at all times the lowest utilization path, the path whose maximum link utilization is the smallest among all such paths. So here I'm showing an example where the network has utilization statistics on each of the links. And you might imagine probes in the reverse direction that are keeping track of the highest link bandwidth seen so far, noting that now the bottom path has a worst case link utilization of 50%, which is higher than that of the upper path. And that would allow the switches in real time to be able to direct traffic on the better performing path and then adapt quickly if that happens to change. So I mentioned these three examples, and the reason I'm talking about them is they're possible today not because the ideas themselves are actually all that complicated, but because the capabilities are now there in the programmable network devices to support this efficiently at line rate. So the emergence of programmable data planes, programmable with languages like P4, allow us to do flexible parsing of packets and do simple match action processing on them, dictated by which fields we've chosen to parse and what actions we want to perform. And to do simple arithmetic and logic operations, and even keep a small amount of state across successive packets so that we can implement measurement functionality, firewall functionality, customized forwarding functionality, and so on. So why is this interesting? Well, it's partially interesting because we unfortunately don't have all the resources we'd like to have. These high-speed programmable devices are flexible, but they don't compromise speed or power or chip area to achieve that flexibility. And so in practice, there's a limit in how much you can parse, how much you can extract out of the packets, how many rules you can use to specify your policies, how much memory you have, and how many times you can access it for a given packet, and so on. And so the real challenge here is to figure out, can we actually do these more sophisticated network control loops while observing these resource limitations? And to me, the key thing that's exciting is that even though these hardware devices are fairly limited in their capabilities, many important network control applications don't need perfectly accurate analysis. It's often the case that approximation is just fine. If you're trying to find microbursts, you don't need to know the size of every flow, just the large flows. And you only really need to know roughly how big they are. You don't need to have a completely precise answer to take the right control action. If you're trying to detect and mitigate DOS attacks, you need a rough count of the number of sources that are communicating with the victim for the victims that have a large number of sources communicating with them, but not for all destinations. And you don't need that count to be perfectly accurate. You just need to know if it's pretty big. And similarly, for path performance, you want to know if one path is better than another, particularly if it's a lot better than the other path. But the estimates don't have to be perfect to be able to get better performance by directing traffic on the better path. And this makes it all a perfect storm, because these approximate data structures can fit within the resource constraints of the switch, using ideas from the long-studied ideas in streaming algorithms from the theory community, adapted to some of the peculiarities of these packet processing devices. Sketches, caches, and so on provide an opportunity to take control action in an approximate way to be able to quickly adapt to congestion attacks and so on. And what to me is exciting about all this is that the pieces are gradually coming together. I just showed you 3-point problems and 3-point solutions. I didn't go into a lot of detail about the data structures in the interest of time. But I think what we're starting to see across the community broadly is a lot of work on problems of expressiveness and problems of scarcity, making it possible to express more and more sophisticated tasks we'd like our networks to do, measurements we want them to collect, actions we want them to take, efficient data structures that can approximately support the things the languages are specifying, and the emergence of hardware of various stripes, whether it's ASICs or FPGAs or even software, general purpose machines that offer regular software capabilities. It's finally possible to bring those 3 pieces together to be able to take those high-level programs and run them efficiently on a wide variety of network devices. And this is what gives me hope that eventually we can achieve this higher level goal of being able to tell the network what we wanted to do and to synthesize the measurement, the analysis, and the adaptation we want from the network in such a way that we can generate the distributed software, hopefully correct by construction, that will realize the control loops we need to run the network the way we want. In short, my hope is that we will eventually be able to tell the network what to do. I'm happy to stop there if there are any questions.
So again, I'll request the attendees to post any questions into the Q&A panel.
Jennifer, there is from the chat, who would resolve the conflict between core network manager and edge network manager in the context of self-managed networks?
Right, that's a great question. I've been thinking about this in the context of individual networks thus far. I mean, you could imagine a single edge network or a single core network. I think once you have multiple networks that need to interoperate, I think there's two ways to think about it. One is to define some sort of protocol for them to communicate amongst themselves. And the other that's perhaps more appealing is to view that each of those networks offer some network slicing or virtual network abstraction that allow end-to-end control over the traffic for one party. And I think we're getting close to that. I think we're getting close to the point where most traffic traverses just one or two networks to go from the content to the eyeball. And as that convergence takes place, it becomes a bit easier to think about the inter-domain applications of programmable networks, where you might imagine the eyeball owner or the content owner having say over the end-to-end path, including say over the virtualized resources of parts of the infrastructure they don't own themselves.
Yeah, perfect. So thank you, Jennifer. And I think we'll take the rest of the questions in the final session.